Hello, so I'm Romain Duballet, and I work at École des Ponts Paris with Olivier and Jean-François and Romain who talked before. And so my PhD is on a building system associating with concrete extrusion. And it's a PhD done between Navier and PIM Laboratory and with Lafarge-Holcim. So the project started 3 years ago. Actually, it had been published in the DMS 2015, and we had presented a work on concrete extrusion or concrete printing that aimed to print functionally graded material with polystyrene beads. So basically, it was quite the beginning of our work, and the idea was to be able to put the material where we wanted, to give some thermal insulation properties additionally to the structural properties of the concrete. It led next to the Democrete project when we formed a great team with different actors, and we also we started working with Lafarge-Holcim, who helped us formulate a correct concrete for the extrusion process, or here again a printing process. And we produced this wall that was meant to be a formwork, so a building part, not a whole building, and the complex structure inside the wall would allow a great reduction of thermal bridges, and so enhancing the thermal insulation properties of the wall. This project led us to form X3. You can see some of the things that we have printed here in the DMS, and I will strongly agree with what has been said about 3D printing in the previous keynote. We don't know yet what we're going to do with it, and printing for now is basically associated with printing sheds, concrete sheds in the world, so nobody has proved what is very interesting about that printing process for the building industry. So basically, I think it will be more building parts, and we have to define exactly what we want to mean with this technology for the building industry. So in a different paper, we have tried to think from the building system point of view and not from the printing process point of view, what would be the possible building system associated with concrete extrusion system. So we have isolated some parameters to do a mapping of the different possibilities. So the two first parameters can be the extrusion scale and the object scale, which will truly impact the decision made for a certain system. And then you have the three other parameters, which is the environment where you intend to extrude your concrete, the different assembly strategies that you can have of external element, of already printed element, and then the support strategy that you can have to help you print your concrete, and not only stacking layers of concrete on top of each other. So all of this make like a huge five-dimensional space of possibilities that we have tried to link with an associated minimal robotic complexity that you would need to achieve each combination. So I wouldn't enter in the details because it's not the purpose of this talk, but we have explored and mapped all these possibilities, and from this work came the idea of what I will present now. It's a building system and not specifically a printing process, but we extrude concrete, or more precisely, we extrude mortar to build confined masonry walls. So the idea of the process is to use two robots. One robot will be a pick-and-place robot that will take insulation blocks and bring them to inside the wall, and on these blocks we'll be printing the mortar. So the blocks will be used as support for the printing, which is very easier to do if you have such kind of help, and the block will provide thermal insulation at the end. So the key for this is to see the wall as a space tessellation structure. So the tessellation here, you have a duality between the two things. So the blocks are polyhedrical shaped insulating material, and between the blocks, on each edge of the blocks, you print some mortar. So the mortar will form a space truss, which is a very efficient structure from a mechanical point of view. And in the negative space, you have the insulation. So you can hope to have a very light masonry wall that has also insulating properties. So you fabricate the block, for example, with a hot wire process, but you can imagine any kind of material, any kind of way of making them. But the main point for this is that on the edge of the polyhedra, you mill and you form a little pipe that will allow the concrete to go in when you assemble them, just as seen previously. So this is ought to be a confined masonry method. So as a reminder, confined masonry, it works with a frame of reinforced concrete, and inside the frame of reinforced concrete you have blockworks and mortar. And the blockworks and mortar system has no reinforcement in them, it's purely concrete, and so it's only meant to act as a wall, firstly, and then from a mechanical point of view to allow solid continuity to help bracing the reinforced concrete. So it is very practical and widely used as a building system, mostly because it's very easy to implement. But from a geometrical point of view and a mechanical point of view, the blockworks and mortar system is very inefficient because you use a lot of material just to allow solid continuity between your frame. So if up to a point, we could say that only the mortar is necessary to give the mechanical strength that you would need for such a wall, which is basically nothing, just resisting the wind and blocking someone from getting into your home. So if you use a geometry like a space truss, it would be very much lighter and very much more efficient. So that is the main point here. So the process decomposed like this. First, you make your blocks, insulating blocks. Here we will use in our laboratory a hot wire cutting process and to cut insulating foam. Then you have the assembly that is done by 2 robots, ideally. So basically, it's a layer by layer process. You put some insulating blocks. You extrude the mortar on the edges of the blocks. Then you put other blocks. You extrude the mortar, and it goes on and on until you have your wall. So this is kind of a generalized idea of 3D printing outside of just stacking a layer of concrete together, and it's because it contains much more complex assembly and support strategies. And at the end, just like traditional confined masonry, you mold your confining elements, and so you can do this. So we had to choose carefully which kind of space tessellation would be the most appropriate for work. So firstly, it has to be printed. So even if we have the support, vertical bars inside the wall would not be very clever. So we have isolated those 5 possibilities for choosing the kind of space tessellation we wanted. You can see here the node valency, the maximum node valence that you can have at each node, And of course, the lowest would be the better, because it would considerably ease the process of fabrication. So we have compared those 5 candidates into a multi-objective approach, because we want this to be printable and we want this to be mechanically efficient and also thermally efficient. So to do this, we have fixed some goal performances. So we fix the size of the wall, we fix a target insulating U value for the wall, and we use no reinforcement, so purely mortar, so a maximum tensile stress which is very low. And we make some parameters vary, the type of space tessellation as I've just shown, and then the bar diameters and the overall thickness of the wall. Making those parameters vary, we set up 3 objectives for our optimization, which will give us a 3-dimensional space inside of which we will choose the best solution. So the first objective is the needed additional insulation that you need to have to your wall. You want this to be as little as possible. The second objective would be the overall mechanical performance of your structure. Among different criteria that could be used, it turned out that the maximum tensile stress in the structure would be the critical one, which is kind of logical, given that we have a very low tensile strength. And the third objective is the surface equate. So all of these objectives we want then as little as possible. So we want to be as close to 0 as possible. So for each type of tessellation, we have gathered some different solution, and you can see here the Pareto front. So all of those points are optimal solutions in terms of our 3-dimensional objective, and then we have to choose among them which are the best. So this is the result for one of the tessellation. Here you can see all the results. Here you can see only in green those that doesn't break the maximum tensile strengths that we had defined. And so in this zone you have the best solution for this specific tessellation. So we did this for all of 5 candidates. It gave the result. And basically we have been able to eliminate some of them. So this one was it has a very high node valency, so it was very heavy. So it's not the right one. This one that would be the most interesting because it has the lowest node valence. It's very inefficient, and the 3/3 are of comparable performances. So here you can see the triangle prism one that I've just eliminated, and all of the 3 here are of comparable performances for our 3-dimensional objective. So basically we chose the one with the least node valence, which is a space tessellation made of semi-octahedra and tetrahedra, basically what I've shown at the beginning of the presentation. Our system can be compared to other concrete systems that are currently used in the industry. So the first one would be the breeze blocks that I've shown at the beginning in traditional confined masonry. You can have also a solution with cellular concrete, which is quite trendy today to give thermal insulation properties to your walls. And you have also the pre-wall system, which consists in 2 insulating walls to build a formwork. You pour the concrete in it, and then you have a prefabricated wall that have insulation properties. If you compare the overall performances of the 3 systems, the system that we have here is of comparable performances, but is very light in terms of the amount of material that has to be used. So it is quite interesting. So we are now, as we saw in the keynotes, equipped in our laboratory to do collaborative robotics printing. So we are now starting to prototype those walls. And it's for now only, I mean, it's okay, but it's only like confined masonry, so Eurocode 6 verification, but if we have an extrusion process able to give some tensile strength by any mean in our concrete, we would be able to check those structures with Eurocode 2, so as reinforced concrete, and we open up to a very large possibility for application of this generalized printing approach. Thanks for your attention.
Thank you, Romain. And we have time for one or two questions. Yeah.
Unless you want to eat.
Hello, can you hear me?
Yes.
You chose 5 patterns for your geometries,
Yes.
and it looks like it's crystallography, like the same geometries that rocks have, like small-scale geometries of atoms in rocks.
Yeah.
The question is, did you study different kind of rocks to have information about their density, their compression resistance, before choosing these 5 patterns?
No, basically we chose among the all regular space tessellations that exist. I mean, among the main regular space tessellations, we eliminate those that would not be printable because of node valency or too many vertical bars to have those 5s. But we worked with very regular space tessellation.
So do you reach
I'm Louise.
Speak loudly.
Hello. I just wanted to know, have you been able to study all the shapes you could do with those? Or are you just considering for now the flat and straight
For now, we are
walls?
doing flat masonry because mostly when you build your house, you want your walls to be flat, so it's not necessarily the main point in the building system point of view. But yes, we will extend the geometry also because those meshes enter into the Romain PhD case that has produced ways of making complex geometry with special meshes that can be buildable. So yes, we will look into this.
Yeah. Have you sort of reaching the similar sort of heights, or could you possibly exceed the heights that you reach with normal masonries in terms of compression capacities, bending out of plane?
Well, it will very much depend on the way we print it, I guess, and it will very much depend on the material because you have a subtle way of formulating your concrete. Because, for example, if we would use we couldn't pour concrete inside such a mold because the mold wouldn't be strong enough. But if we print concrete, like we print on the different object, you gain some performances right when you print it. So if you formulate your mortar to have a specific curve of gaining mechanical performance, and you play with the process and the strengths also of the different blocks, because you can if we for the blocks, for example, we use something like mineral foam, you can have a very wide range of properties between mechanical strength and thermal properties. So you can be very fine, and I guess you could reach very high heights. But for now, we have not so much looked into this.
Thank you. So this was our last presentation on the session. Thanks again to Romain.